Hi everyone, welcome to lecture. As usual, we'll start with some announcements. First thing, contest 2. I'm sure the last thing any of you are thinking about at this moment with the midterm on Monday, but the code and instructions for getting started on contest 2 have been released. You can look at those on edX. The website where you submit your bots and they play against each other is still, the uploads are not open. It's still just showing the results from contest 1. We're going to leave it like that for just a couple more days. You'll have, actually don't remember the due date. I believe it's a week from this Sunday is when contest 2 closes. It might be a bit longer, but it's at least that long. So you'll have some time to do this. And recall that we only had 9 submissions and we give extra credit to 10 people. So you really should at least make something. You'll have a pretty good chance of getting that extra credit. Yeah, just a reminder again, midterm next Monday, 12 to 3 p.m. in 155 Grinnell. I don't know if we had actually made it very easy to see where that room was beforehand, but now, 155 Grinnell, that's where that's happening. And we released a practice midterm. You've probably seen the announcement on Piazza, and it's due Saturday at 11:59 p.m. on Gradescope. In the initial announcement, it said edX. That was a typo. It's there's an assignment that you can submit to on Gradescope. If you haven't yet been enrolled in Gradescope, you should have been. Please email us the staff list as soon as possible. Other news is we're going to have a student-run review session / study party this Friday. We were thinking about trying to have a normal one that's led by a staff member, but we're all stretched pretty thin, what with writing the midterm and everything else that we're already doing. We couldn't find the time for one of us to actually make a worksheet, prepare for that. But we had a student volunteer to help out in running this, so that'll be in the Wozniak Lounge. The number I think is 430 Soda, for anyone who doesn't know where that is. And 2 to 4 p.m. on Friday, it'll just be work together in groups on old exam problems. I think there will be a worksheet printed out for everyone to take, or at least posted somewhere. And I think that is a great resource. Anyone who is free at that time, that would be a great way to study for the exam. And then, big announcement, the final exam, when we did get the time from campus, we got 11 to 2 p.m. initially, 11 a.m. to 2 p.m., and that conflicted with finals for a bunch of other classes. We managed to get that pushed back an hour, so you're still going to have back-to-back finals, unfortunately, if that affects you, but at least they don't conflict. With this change, if anyone still has conflicts with the final, please email the staff list about it as soon as possible. Questions about announcements, logistics?
You have a room for the final? Or not yet?
We do have a room, but I don't know what it is off the top of my head. I think it's posted on Piazza. If not, you'll know with a lot of time in advance where that'll be. Any other questions? Yeah?
Did you press report today?
I did, actually. Can someone vouch for me? You saw me do it? Yeah, a few people nodding in the front. I made sure I had witnesses. Thanks for the reminder, though, just in case. Okay, so let's move on to the content. And we saw the first half of this slide yesterday, which was part 1. We finished, which was agents, planning, search, everything that we've done up to now. What we're moving into now is probabilistic reasoning. So in this section of the course, we're going to be given some kind of probability model, all the information we need to know about how different things relate to each other, and there will be randomness involved. And then we want to come up with some kind of inference, make useful decisions based on all of these noisy observations we might make or partial information we might have. And some examples of where you'll see this, examples that we'll go through in lecture. This is a really useful one as an intuition for what we'll be doing next week, diagnosis. If you have some complicated relationship between a bunch of different variables, say for medical diagnosis, this would be, does someone have a history of an illness in their family? Are they showing symptoms A, B, and C? And do they have this disease? Then there's some relationship between all of those variables. And if you know some of those things, you want to be able to make the most informed decision possible about whether or not they have the disease. That's usually in that particular example what you're trying to figure out. Other kinds of diagnosis that aren't medical are if your car is not starting, then I don't know a lot about cars, so I can't list very many variables, but there are all sorts of different things that could be wrong with your car, different things that could be causing those, and we have probabilistic relationships between all of these variables. If we know some of them, we'll have a way to infer what's most likely for what we actually want to know. Speech recognition is another one. We used to have a project actually on speech recognition, but we found that the autograder tests tended to be, you write some code, run the autograder test, and then it gives you a % accuracy, and there's not a lot of feedback. It's not that exciting, but it's totally within the space of what you can accomplish with what we'll cover in the next 2 weeks. And the reason this is so probabilistic in nature is, remember that when some piece of hardware is hearing something, what that really means is it's getting some pressure wave signal, and from that it has to discern meaning. And not everyone talks exactly the same way. People have different accents, they talk at different speeds, and other subtleties in the way people talk. If they misspeak, can you infer what the most likely thing they meant was? That's another problem that we can solve using hidden Markov models. We'll see in a couple weeks. Tracking objects, this is one that we actually have a project on. And that project is, the ghosts are now invisible, and Pac-Man is getting his revenge. Pac-Man gets to eat the ghosts. They're running away, but he can't see them. He can only hear them running around. And so based on hearing them, he has to maintain a best guess about where the ghosts might be. And of course, hearing is not a super reliable way to track where a ghost might be. So you have to do a lot of probabilistic inference to solve that problem. Robot mapping, that's a new project that we just made last semester. And you have some belief distribution when you start out about, or a model, probabilistic model, about what a building might look like. And so if you if you run into a corner of something, you run into some bricks, you think you're probably at the corner of a building, and so you are going to imagine where the rest of that building might be, maintain in your head a belief of what the map looks like, and then walk around in the map to try to gather the most useful information to fill that in. And in that project, there are a few different buildings, and you're trying to find a particular one. They have different things that may or may not be true about them with different probabilities, and so it's the same kind of reasoning. More generally, robot mapping might be getting some visual input, and then with some model of what a wall looks like and geometrically how walls interact, try to figure out where in a room the robot is. Error correcting codes. You might have seen in CS70, if you took that, some professors cover a little more electrical engineering focus in there. But when you're sending messages across any kind of channel, it's some bit string, zeros and ones. But in reality, you're actually sending, voltages or some other continuous value that's supposed to communicate 0 or 1, but usually it's somewhere in between. It's just, if it's supposed to be a 1, it's close to here, 0 over here. But there's all sorts of things that can go wrong. Packets can be dropped, and that signal can be influenced by random noise, so that we have to come up with schemes for how to make it robust to these changes. And the way that we define robust is using probability. We say, we have some model of how likely it is for certain kinds of failure to happen, and we want, with high probability, to be able to withstand these kinds of failures and still get the right message. So these are just a few. We'll see even more. And then if you keep these ideas in mind, you'll probably notice that this kind of reasoning helps with all sorts of problems you might be solving in other areas of computer science. And then just a quick nod ahead to the last part of the course, machine learning. The big difference there is that that is where we're not given an explicit probability model. We have to, like we were doing with reinforcement learning, experience or gather some samples and then build a probability model, come up with our best estimates for how likely things are to be. So let's get started. Fair warning, if you really are sharp on probability, this is probably the most boring lecture of the entire semester, because we are really just building up the tools that we need to talk about the new artificial intelligence concepts that will start next week. But it is important to make sure that you have this foundation. So here are all the topics for today. And most of these, if you've taken a probability class before, should be familiar. You may not remember the specifics of how they work, but they're words you've heard before at least. Random variables, joint and marginal distributions, conditional distributions, the product rule, chain rule, and Bayes rule, and then inference and independence. Those will come in a lot more significance starting next week, but we will talk a little bit about inference as well today. So first, I want to show a demo of one of those examples I was talking about. And this is kind of a simplified version of the chase down the ghost game, where the ghost is not moving, but we still can't see it. Oh, sorry. Let me actually keep talking about the slide before we start. What's going to happen is we're going to get some noisy reading of where the ghost is when we guess a particular spot. What I mean by that is the board's going to start out all blue, no information there, and we click on a square. Say we click right here. Then we're going to get a reading, sensor reading red, orange, yellow, or green. And what those different colors correspond to is how far away the ghost is from where you clicked. But there is some noise involved, because usually if you're trying to model real-world scenarios, like trying to chase down a ghost, there's a lot of noise involved in your sensor. Sorry, that was a joke. You'll notice that there's a probability distribution down here. So that's talking about this square right here. This is 3 away from where the ghost actually is. If we click here, then we know this distribution. With probability 0.05, it'll be red, 0.15 orange, 0.5 yellow, 0.3 green. This is the most likely, which is good, because we're like medium far away from the ghost, and that's the information we're trying to gather from this. So without actually dealing with how to handle those numbers, that's what we'll get to by the end of this lecture. Let's just look at what that feels like trying to track down that ghost. So here's the board. And say I click right here. Green. Okay, so as of right now, my best guess is the ghost is probably far away, maybe in one of the corners. But it's still possible that that was just a bad reading and it's close by. So maybe I'll try over here. Still green. Orange, okay. So now I'm starting to think it's pretty likely it's up there. Let's search around in this direction some more. Yellow, maybe I'll go over here. Orange. Okay, so right now, we probably have a pretty good idea that that red square in the corner is where the ghost is. We can also keep searching a little bit to try to be more confident. And yeah, it seems pretty likely. So we'll bust, and there it is. That's the ghost. So the next demo we'll see, after everything in between is talking about numbers and probabilities, is this again, except we're going to explicitly represent a probability distribution, our belief of how likely it is that the ghost is in each one of these squares. So there will be a number on each square. But for now, we don't know how to handle that. So let's cover that. Here's the general statement of the problem, uncertainty. We have observed variables. So those are things that we know. In the case of the demo that we just saw, the observed variables are those sensor readings, the yellow, green, blue, red, not blue, yellow, orange, red, green. And then unobserved variables, which are aspects of the problem, variables that are relevant to solving this problem that we don't know their actual value. Those are, in that example, where the ghost is, and all of the sensor readings that we didn't take. But most importantly, where the ghost is. And then when we say model, we're talking about the relationship between all these random variables. More specifically, we're talking about the joint distribution over all the variables. We'll talk about that in more detail in a couple minutes. And probabilistic reasoning allows us to put numbers on this and manage in a principled way our beliefs and knowledge so that we can come up with optimal, remember, rational algorithms for solving tasks like this. And later on, we'll even see algorithms that help us make the decisions that will give us the most information. Today, we're just going to be talking about given all the information I have and the model that I have, what is the probability distribution? So I've said this a couple times, hopefully a refresher, but random variables, this is the way that we're going to be talking about probability, is we have some set of random variables, which are something that takes on different values with different probabilities. Some examples could be R would be the name of the variable, and what it corresponds to is it raining? And it can be yes, it's raining, or no, it's raining. It takes on those two values with some probability. Is it hot or cold? Same thing. D, how long will it take to drive to work? Now we're not talking about yes, we drove to work, or no, we didn't drive to work. It's how long. There's some numerical value. That's also totally fine. And where is the ghost? In this case, it's none of those things. There's some set of possible locations, and the values that L will take on is in this position with probability 0.1, in this position with probability 0.5. It'll look like that. So note that we denote these random variables with capital letters, and like variables in a CSP, same thing here. Random variables have domains. We just talked about what these domains for these might be. And here's some important shorthand that we're going to use. Important only in the sense that, for the most part, that's all that we're going to use in CS188. This all generalizes in a pretty unsurprising way to variables with more than two values in their domain. And so we will expect you to be able to do that. But most of the examples we see, because it's usually easier to talk about, will be Boolean random variables, things that are, did this happen? Yes, it happened, or no, it didn't happen. And when that's the case, we use this shorthand, plus r minus r, as the two values in that domain. This is useful both because it tells us whether or not it happened, and in a more concise way, also tells us which variable we're talking about. So we can say things like if plus r something. And then we know we're talking about if, yes, it is raining, then so-and-so. And one thing we aren't going to really talk about in this class is continuous domains. We're not really talking about continuous probability distributions because the math gets a little bit harder. But if you're familiar with how that works, it will generalize in exactly the way you'd expect. So if you have questions about that because you want to know, feel free to ask us about it. But we won't expect anyone to be doing integrals in this class. So that's a star topic. And associated with every random variable is a probability distribution. So if our random variable is temperature, and it can take on values hot or cold, then in our model, we'll say there's some probability that T equals hot and some probability that T equals cold. And usually, this is the way that we will choose to represent that, is in a table like this. So these tables, you're going to see a lot of them. And so you'll want to get used to organizing information in this way. You've probably seen this before, but in a lot of introductory probability classes, this isn't the end-all be-all notation. Here, this is pretty much what everything is going to look like. So yeah, probability tables. What's happening is, if I'm saying that with probability 0.5 it's hot and probability 0.5 it's cold, then we have a row corresponding to those two possible outcomes for the random variable, a row for each one. And then over here, just what probability is that outcome. And then here's another example, not a binary random variable. There are 4 values it can take on. The weather is sunny, rainy, foggy, or a meteor shower. 4 things we have to worry about when we're deciding what to wear. And this is what that could look like. Again, a table with 4 rows, 1 for each value in the domain, and then a probability on the right side that is how likely that outcome is for that random variable. So let's talk about probability distributions. These are the same 2 tables from the previous slide. And for the sake of this class, this isn't exactly like a mathematical statement, but we're going to be using these probability tables so extensively that it's useful to think of the probability table as the distribution itself. And of course, all the information we need to know is there, right? If we're only talking about how likely is each outcome for temperature, then the table tells us everything we could possibly want to know about that. And so we will say is a table of probabilities of values. And what that really means is later on we're going to be writing things like P of t times P of w given t, something like that. And this looks like an algebraic operation, and in fact it is. But when we write P of t, that actually refers to one of these tables. And so we're going to redefine multiplication to be an operation on tables. That's called a table join, and we'll see that next week. But for now, yeah, a distribution and a table, same thing in this class. And yeah, we already really looked at this where variable W, capital letter, and the values it can take on in its domain, it's going to take on one of those probabilities with some real valued probability, and we have a couple of constraints on what that distribution looks like, which are that. So these are two axioms of probability distributions. By definition, no event, no outcome for our random variable can possibly have less than 0 probability. 0 probability means it can't possibly happen. Less than that has no meaning. Probability doesn't allow that. And the other axiom, thing that we require for anything to be a well-defined probability distribution, is that all of the probabilities of different outcomes for a random variable equals 1. And 1 is an important number in probability. 0 means it can't possibly happen. 1 means it definitely will happen. And so an intuitive interpretation of what it means to say the sum of all of the probabilities of each outcome for a random variable is 1 is this random variable must be one of those outcomes. And so if we're adding up the probability of all of these, oh, sorry, I changed that because that's probably more realistic. Probability meteor is 0. Anyway, back to the point. The probability that any one of these outcomes is the true one for this random variable is the sum of all those probabilities. And that must sum up to certainty, because with certainty, it will be exactly one of those things. And this is another shorthand we'll use. So this is the actual explicit way of writing out what we mean. Probability that the variable w takes on the value rain. And we're going to use this shorthand in a lot of cases. Now, note that this doesn't make sense if we have two different random variables that can take on the same value, because then p rain, if there's w1, weather on day 1, and w2, weather on day 2, it's not clear if we're talking about the probability that it rained on day 1 or on day 2. So we're going to use this shorthand whenever we can, and the reason it works is only if all domain entries are unique, if our two variables have nothing in common in the names of all of these outcomes they could take on. So the next thing we need to talk about is joint distributions. And now what we're doing is going from one random variable that can take on these possible values to expressing relationships between different variables. If we have two different variables, then every pair of outcomes for those has some probability assigned to it. And you may be thinking of an example like, what if we flip 2 coins? Then can't we just multiply the probabilities together? Well, that's a special case, and that's when they're independent random variables. But we could have something like what I just said before, weather on day 1 and weather on day 2. It's pretty likely that if it's sunny and warm on day 1, it's just more likely that it will be sunny and warm on day 2. There's some relationship between those two events. They're not independent. And so in order to numerically capture what this relationship is, the best tool we have right now is a joint distribution. And so that'll say, for the outcome, sunny on day 1 and sunny on day 2, that's more likely than just the two of them happening independently from another. And that'll be just represented as numbers in this table. So in the algebraic notation, probability of variables equal to values, it looks like this. And again, this is the explicit form. We will often use this shorthand where same caveat. As long as the names don't conflict with each other, it's pretty clear what we're talking about. And we'll put it in a table again. Now our table looks a little different. We have more than 2 columns. We have a column for each variable that we're considering in our joint distribution, and then 1 column again at the end that is the probability of both of these happening. So this row corresponds to the probability that the temperature is hot and the weather is sunny. And of course, as you'd expect, that's more likely than the temperature being hot and the weather being rainy, which is 0.1. That's what I mean when I say these numbers are going to encode all of these relationships. Is same thing down here. When it's cold, you can see that it's more likely to be sunny than rainy. We'll talk about those things, put names on those kinds of observations pretty soon, conditional probabilities. But again, we have some axioms that a joint distribution must obey. So it's a little bit hairier now, just because this is a longer equation. But first of all, the probability of any configuration of all these variables, any outcome, we call it a joint outcome when we assign one value from each domain to each of those variables. No probability, again, can be less than 0. That doesn't have any meaning, and we require that this is true for any distribution. The other thing is, if we consider all joint outcomes, another thing that you might hear us say is joint instantiations of all these variables, then they sum to 1. Same reason as before. And all that looks like over here, if we have a joint table, is that all of these numbers in all the rows sum to 1. This is all of the possible configurations, instantiations of these 2 variables. And we have 0.5 up here, 0.5 down here. Okay, so before we move on, any questions about joint distributions or the table notation? Because this is pretty important. Okay, so what is the size of a distribution if we have n variables with domain sizes d? Think about that for a second. So we have now n variables, which means n plus 1 rows in the table, and then each of them has domain size d, and we need to consider every possible assignment to all of the variables. Someone have an idea how big that will be? How many numbers we're keeping track of at that point? Yeah. Yeah, exactly. D to the n. So when we have just one variable, there are d values it can take on, and we need a probability for each one of those things. Just d. When there are 2 values, we have to consider 2 variables, excuse me. We have to consider the d values that the first one can take on, and for each of those, the probability that the second variable will take on each of its d different values, and so on and so on. We end up with this number d to the n. We don't like d to the n because anytime we have something like n in the exponent, that means that the more and more variables we add to our system, the more it's going to grow exponentially in terms of the space complexity of even just keeping track of this joint distribution. When we're talking about small, simple distributions, this is okay, but as soon as we are doing medical diagnosis systems or things like that, that in reality usually have hundreds of variables, this is impossible. And so we'll see different ways of specifying probability models, different ways of communicating all of these relationships between variables that use less space next week. For today, we're going to kind of sidestep this problem and just only look at distributions that are small enough to work with in this way. But keep in mind, for real problems, this doesn't work. And that's the problem we're trying to solve next week. So I keep saying probabilistic model, kind of equating that with joint distribution. And as of right now, they are equivalent. When I say probabilistic model, another thing I've said a couple times is it specifies all of the probabilistic relationships between different variables. And of course, if we have every single one of these probabilities for every pair of outcomes, then that's sufficient to tell us all that information. And so a joint distribution, a joint table like this, is one example of a probability model. Next week, we will see a Bayes net that is more explicit in that it specifically gives us the information about the relationships between pairs of variables. And then from that, we are able to do a little bit of work to recover a joint distribution if we wanted to. So for now, our probabilistic model is a joint table. Other kinds of probabilistic models are any form of lesser information, or not lesser even, just any piece of information you can give me such that if I needed to, I could recover any row from this table. Basically, other implicit representations of the joint distribution. Notice that this is kind of like a constraint satisfaction problem, where again, we have variables and domains. And I want to talk about for a moment what it would be like to think about CSPs in the way that we're doing this right now. Remember with CSPs, we drew the constraint graph, and then we said there are constraints on pairs of variables. And then we came up with some algorithms to deal with those pairwise constraints so that we could come up with a full assignment to all the variables. A joint table or I'll highlight this one. A joint table for a constraint satisfaction problem is like, for every assignment to all the variables, is that a satisfying one or not? Now, of course, that gives us the information that we want to know, which is how do we get a satisfying assignment that doesn't violate any constraints, but it's really overkill, blows up in complexity in the size of the problem really quickly. And so the way that we did something more clever here was break it down into smaller pieces and come up with algorithms that dealt with other representations of this information. That's exactly what we're going to do next week. So that's kind of a preview. Now we're back into probability plumbing. Events. This is just another kind of important vocab word in talking about how probability works. And an event is a set of outcomes. Remember, we defined an outcome as some, well, I said joint outcome before. When we say outcome, that's what we're referring to. Some assignment of all of the variables, some value from their domain. So something like x1, x2, all the way up to xn, which implicitly means the variable x1 gets this value little x1, etc. That's one outcome. And an event is a set of different outcomes. Now notice that the way we've defined outcomes for this course, no two outcomes can happen simultaneously because an outcome two different outcomes require one random variable to take on different values. And so with this definition, we also have this formula right here, that the probability of some event, some set of different outcomes, is the sum of all the individual probabilities. That's useful, a useful way to define it. There are other ways of axiomatizing probability, maybe that you've seen in introductory classes, where you have to be a little more careful about this. But with our definitions, this is totally true. There's no way that two different outcomes can coincide. So we're talking about a bunch of disjoint events, and we can just sum up their probabilities. Which means, from a joint distribution, we can calculate the probability of any event by just summing up rows in the table. So let's look at an example of that. If we have this table, same one we've been looking at, what is the probability that it's hot and sunny? Well, that's a pretty simple event because that's just one outcome, assignment to all the variables. Hot and sunny is this row in the table. And so that's 0.4. Probability that it's hot requires a little bit more work because now we're talking about the event, the set of all outcomes in which t is equal to hot. So it's not just this one, it's also this row. And so how do we get the probability that it's hot? Sum those up. 0.4 plus 0.1 is 0.5. And then a little bit more work to calculate this last one, the probability that it's hot or sunny. Now we're talking about all of the outcomes in which either of those are true. Again, we can just point to which rows in the table is this talking about and sum them all together. So here's another one where it's hot. Here's another one where it's sunny. So those three together are all of the outcomes in which it's hot or sunny. And remember, this is logical or. So both of them happening is fine too. And so what's that probability? 0.7. Yeah, great. And yeah, so typically the events that we care about are partial assignments, like probability t equals hot. And so to get them out of a joint table like this is the process that we follow. So now I'm going to make all of you do what I just did for some different numbers. So take a minute or two to work this out, and then we'll come back to talk about it. And feel free to talk if you need to your neighbors. Okay, actually we are getting behind a little bit. I'm going slower than I meant to. So I'm going to cut that short a little bit. Hopefully there's not too much to be done here, so you were able to at least figure out what you would do if you weren't actually doing this out on paper. So to get this, what do we do? Someone raise hand? Yeah. Yeah. Probability of this outcome plus x plus y. Just get that entry in the table. It's 0.2. What about this one? All right, I'll just talk because we got to kind of speed it up a little bit. So we need to consider the other outcomes in which plus x can happen. That's these two rows right here. And so we have 0.5. And then just like before, minus y or plus x, we now just need to also consider this other outcome with minus y. Note that we have that one already accounted for with plus x. And so those three summed together is 0.6. Okay, so marginal distributions. All a marginal distribution is if you have a joint distribution over 5 variables, a marginal distribution is your distribution over some subset of those variables. Usually, the most common thing that we're concerned with is, like what we just saw, getting it in terms of one of the variables. So the way that we do this is by adding rows together, and we'll see a couple examples. We already really did this with the hot example. And then the other thing to keep in mind is when we have two variables, t and w, we can get a marginal distribution for t, like that, but there's also a marginal distribution for w. And if we had more variables, we could get the marginal for any of them in the same exact way. Sum out those rows. So I want to take a moment to highlight this formula because this is something that may not be, when we're looking at a table, it's kind of intuitive. But in the algebraic form, this is something pretty important and a pattern we'll keep seeing. We call this summing out. And basically, if we consider all values in the domain of some variable and sum over those, the joint, we end up with that variable taken out of the joint, essentially. So going from p of t comma s to just p of t, we sum over all the values of s, and then s is gone. The intuition behind that is building it up from this way of thinking about tables that we've been doing. But for now, if you're struggling with that, just try to remember this pattern, and hopefully it'll sink in after a while. So yeah, I'm going to skip this. Because, yeah, if you're interested, you can come back and add those numbers together. But for now, let's move on to the next topic, which is conditional probabilities. So this right here is a definition, which means everything comes from this. We didn't derive this from anything, but there is an intuition for why it's defined this way. So conditional probability means, given that I know B, how likely is A? What is the probability of A? And this is a diagram that might be helpful in thinking about that. We say this red circle is all of the outcomes in which the event B could happen, and the blue circle is all the outcomes in which the event A could happen. Since these are sets, they might have some some intersection, and that's what's in the middle here. That's when both A and B happen. And so if we say, given that we know B happened, given that we know we're somewhere in this circle, what is the probability that A happened? Then that's just this area, this intersection, divided by the area of the whole circle. And that's how we get this. This area right here is probability of both A and B, and the whole circle is probability of B. So here's our joint table again, and we want to know what is the probability that the weather is sunny given that the temperature is cold? Well, we're just going to plug into that formula again. And the way that we do that is probability of, I'm going to use the shorthand here that I talked about, just S and C instead of equals like that. S comma C over probability of C. How do I get S comma C? That's just a row in the table, cold and sunny. So that's 0.2. How do I get P of C? We have to sum out in the table, consider all of the rows in which the temperature is cold. That's this and this. So that's 0.5. So we have 0.2 over 0.5. And you can kind of see in the table what that looks like. We're just considering a part of the table, and then out of that part, what proportion of the total probability does this row take up? I'm going to have to fill in. I'll leave these quizzes as exercises for you to do later. We have some more involved ones a little bit later when we get to Bayes' rule. But what's important to note is that if we're considering now something like probability that the weather is sunny given that the temperature is hot, and same thing for the weather being rainy, we actually end up with another probability distribution. And so we can put that in a table in the same exact way. And conditional probability tables, we'll just call them CPTs for the most part, are just as important as these joint tables like this. The way this works is sometimes we write it like this, where it's W and P. Another way that we'll sometimes write it is W, and then we'll be a little more specific about what we mean. Probability of that W given T equals hot. And then we fill in those numbers, same exact way. So that's a conditional probability table. Once again, looks like this. Just each row corresponds to one outcome, and then the probability of that outcome. And we can do the same thing for T equals cold. Together, we can actually even put these two tables together, and if we do that, then we get something a little bit more complicated, which is probability of W given T. And we're literally just going to stack these two tables on top of each other, sort of. So now there's a row for T, W, P, and we say T hot, hot, cold, cold, sun, rain, and just fill those in with those same values. So that's 0.8, 0.2, 0.4, 0.6. You might be wondering at this point why we'd ever want to do that. For now, let me just tell you, you're going to see this, and then at that point it'll be clear why. So you'll want to have seen it before, where sometimes instead of the smaller tables, we stack them together. And it's just kind of a more useful way of keeping track of everything. So one other point, just a quick side note about summing out when we have conditionals. It works the exact same way, and here's a little algebraic proof of this fact, where if you have the probability distribution of A given some outcome of B. So we're considering this distribution now, and you sum over all the values of A. Well, with the formula I told you before, it's not totally clear what should happen. What happens when A disappears from the distribution? Well, it actually just sums up to 1. And here's why this happens. You can take a look at this, maybe come back to it later if you're curious about how the algebra works out. Another intuition for it is, again, if we're considering only the outcomes in which B happens, then the two events, if we sum over the values A could take on, are yes, A happened, which happens in this region in here, or which is yes, A happened and B happened, or no, A didn't happen and B happened, which is this region over here. And since we are dividing by the probability of B, dividing by the area of that circle, we're essentially just adding up the two parts of that circle and then dividing out. It's just 1. Yeah. And a trick called normalization. This is another thing where it looks like we're taking things that follow pretty immediately from what I've already taught you and just reiterating them. But we're going to kind of abstract away the details of what we're doing here a lot and just say, now normalize. And so it's pretty important that you know what we mean when we say, now normalize the distribution. So the first thing we need to do if we're trying to go from a joint distribution to this conditional distribution, W given T equals C, is look at the rows that are consistent with this evidence, this conditional T equals C. So we are only looking at this part of the table. This table is going to have 2 entries, right? One for the weather being hot, given that the temperature is cold. Sorry, the weather being sunny, given that the temperature is cold, and one for the weather being rainy, given that the temperature is cold. So let's compute that first one. Probability weather is sunny, given temperature is cold. We plug that into the definition of conditional probability, which is just the joint outcome over the marginal outcome, PT equals C. We get T equals C by summing up these 2 rows of the table. Looks like that. And when we plug in those numbers, we get 0.2 over 0.5 equals 0.4. We do the same thing down here. We're considering now probability that the weather is rainy, given that the temperature is cold. That formula, once again, the definition of conditional probability. Sum things together to get this probability of T equals cold. We have this expression, plug in the numbers, and we have 0.6. And now we have our table. So the question now is there something more clever we can do to get from that table to that table? Notice that we kind of repeated some computation in there, that this sum right here is the exact same sum as this one. So we only really need to do that once. And one other thing that's kind of interesting is this sum right here. What this corresponds to is taking this subsection of the table and summing up all of its entries. Now, why would I even point that out? Well, let's look at breaking this down into 2 steps in terms of look at this relevant part of the table and then just work with that. Select the joint probabilities that match the evidence. And so now we have this table. And this is not a full probability distribution, right? Because this doesn't sum up to 1. This doesn't have a row for every outcome. So we need some naming convention for what this is. And this is what we call it. Probability of lowercase c, comma, w. It's a piece of the joint distribution. The rows of that table where T equals cold. Now once we have this, remember that the distribution we ended up with was 0.4, 0.6. We just needed to divide both of these values by this sum that appeared in both places. Well, that sum is actually just the sum of the probabilities in this subtable. So instead of thinking of that as plug it into this formula right here, we break it down into this normalized step. We just say, make the probabilities sum to 1. And of course, what that really means is get the sum and divide by the sum. But it's useful for us to have this word normalize, which means go from here to here. And that'll come up over and over and over. In my experience teaching this class, we show this slide. Everyone gets it when we show the slide. And then by the 3rd time it actually shows up and we say normalize, people have forgotten what we even mean by that and they stop thinking about it. And then in time for the final, people say, wait, what exactly does normalize mean? So it seems kind of trivial, but just try to keep this in mind. Don't let it slip too far away when we start saying normalize. Why are we doing that? Why does it work? What does it mean? Okay, so yeah, we are a little bit behind on time, but not too bad. So I want to take this moment. It's kind of weird timing just because of the way the lecture schedule worked out, but I do want to get some feedback about the course so far. So first thing I'm most curious about, feedback on lectures. That's for me specifically. Talk faster, talk slower, get a haircut, these kinds of things. But we also want to know about how you're feeling about every other aspect of the course, discussion, and that can be TA specific or about the way discussions are organized in the course in general, homework projects, and anything else that you want to tell us about. Right now I'm struggling to open a pack of index cards. Okay, got it. And so I'm going to just, walk out of the room so there's this air of confidentiality and pass these down. You start passing these around. Hopefully you have some writing utensils. If not, try to borrow one. And we'll take like 5 minutes to do these, and then I'll come back in. Before I go, last minute questions about anything we've seen in this lecture so far. Okay. Who's still working just to get a sense, writing stuff? Okay, it looks like few enough people that we should move on. But yeah, I just want to say this is intended to be anonymous. If you wrote your name on it, I mean, that's okay. I don't care. But just for the sake of, if you wanted to say something mean, I want to hear that if it's, valuable feedback. So once again, at the end of the lecture, I'll walk out and everyone can bring those up. I didn't want to do that just now because that takes like a minute or two. But that way, you can put them all in a stack and they're anonymized. Okay. So the next thing to talk about is probabilistic inference. And we've been doing hints of this for this whole lecture. But now we're going to actually talk about, with the problem we want to solve and the tools that we've looked at so far, an algorithm. And the algorithm that we're going to talk about today is called inference by enumeration. So, well, okay, we'll get to that on the next slide. First, let's specify, again, really concretely what the problem we're trying to solve is. We want to compute a desired probability from other known probabilities. In other words, we have a joint distribution, that's our model, the known probabilities, and we want a conditional distribution. Why do we want a conditional distribution? Well, you can think back to all of those examples I went through on the first slide. For example, we could talk about, tracking. In that case, what a conditional would be, a conditional we care about, if our variable is where is the ghost and what is our reading at each square, then we have a joint distribution over all of these. And when we're actually acting and making decisions, we end up in a situation where, okay, we have these three readings. Given these three readings, what's the probability that the ghost's here? What's the probability that it's here? Etc. Like that. So that's why, in the end, the conditionals are what we care about. So, yeah. Another phrasing of this that you'll see a lot is the agent's beliefs given the evidence. Sometimes you might hear belief state as well. Really, all beliefs and belief state means is what is the probability of all of the outcomes given the evidence that I already know. So, when we are making decisions, trying to determine which of these things is going to be best, maybe whether or not we're on time makes a big difference for something we're trying to decide. When we have this evidence, no accidents 5 a.m., well, there's not a lot of traffic on the road, and so we can expect it's very likely that we're going to be on time. If then it starts raining, this is the conditional probability we're concerned with. We have more information, and so with that new information, our belief of how likely it is we'll be on time gets lower to 0.8. So we're going to have an algorithm that tells us, based on a joint distribution, how to get these numbers. So this is the algorithm, inference by enumeration. Specifying the inputs to the algorithm, we have evidence variables. Those could be like the readings in the sensor model, anything like that. Query variable, what we actually want to know about. And in general, you can have more than one query variable. It works exactly the same, but it's just a little bit easier to show for the first time with one query variable. And hidden variables. So these are all of the relevant details in our model, other variables that are not in either of these sets, the evidence variables or the query variables. That means, for example, in the same trying to find the ghost example, our evidence would be the readings that we've taken, our query is where's the ghost, and our hidden variables are all the readings that we could have taken but haven't taken yet. And with these three pieces, we need to put together a conditional distribution. And all variables are going to go in one of these three categories, by definition. Then this is what we're looking for. So here's the algorithm. Looks a lot like what we've kind of already been doing. Select the entries consistent with the evidence. Remember, we're given the joint table, the big one, with all of the different variables, every single row. And so we grab the ones that have values here matching all of the evidence that we've observed. We sum out all of the hidden variables because we don't really care about them. We don't want them in our final expression. At this step, what we have is probability of capital Q, all values of Q, all values of all the hidden variables, and specifically these values of the evidence variables. In this step, we get rid of all the H's, sum them out, and that's going to look like, oh good, I have it written on the slide, like this, where originally we have the joint over everything, sum over all the h's, and here's that sum out pattern again. When we go from here to here, all the h's, the variables we summed over, disappear. And then normalize. So normalization, if you recall from that slide, takes us from this joint over all values of Q and specific values for all the evidence to sticking a conditional bar right there, essentially. And once we have that, we get what we need. And yeah, this Z, another way to think about normalizing is, well, it's really not another way, it's the same way. But take the sum of all the entries in that table, call it Z. This is just this divided by Z. And when I say divided by Z, that's entry-wise. Every entry in the table gets divided by Z. So there's our whole algorithm. And you know, if you kind of believe me on everything I've said so far, and accept that we've kind of jumped into a more general case with a lot more variables, but everything still works the same, then you should be fairly comfortable with this. That with those three little pieces that we talked about in previous slides, put them all together, and we have a general algorithm for going from the big table to the conditional distribution right here. So now I'm going to give you a chance to try to work this out for a couple examples. So here's a big, like medium-sized maybe, joint table. How do we compute the probability of W? Well, let's just do this interactively because we still have some stuff to get to. This is essentially the same thing we were doing before in computing the marginal distribution. There's no conditional, so we don't have to do that last step normalized, but let's think about the steps of the algorithm. First, grab all of the rows in the table which are consistent with the evidence. That's just all of the rows, right? Because we don't have any evidence. Everything's consistent with no evidence. And then sum out all the hidden variables. Here, the hidden variables are just the ones that aren't W. So we need to sum out S and sum out T. Our two values of W are sun and rain. So let's talk about P sun. We would get that by summing up all the rows in the table where, regardless of what these values are, W is equal to sun. And then that's 0.3 plus 0.4, or plus, yeah, 0.3, 0.4, 0.5, 0.65. And then P of rain, we could do the same thing. We also know, because they have to sum to 1, that it's 1 minus 0.65, 0.35. All right, I'm going to also, let's see. Yeah, we're going to skip this one, but we're going to do this one as well. Probability of W given winter. So same steps again. Select all the entries in the table which are consistent with the evidence. Consistent with the evidence just means the season is equal to winter. So we're now dealing with just this smaller portion of the table right here. In there, we now want probability of sun given winter. Oh, sad. Oh, that's been going on for a while, hasn't it? Okay, it just reconnected. I don't know why that happened. But, all right, I'll write what I had again. This subsection of the table right here, consistent with the evidence, remember, because our evidence is winter. These are all of the entries where season is winter. And we want probability of weather being sun given winter and probability of weather being rain given winter. Oftentimes when we're writing this out by hand, it's a little bit easier not to draw the table. This is exactly the same thing. It's the same numbers represented a different way. But the way we do this is sum out all of the hidden variables, so temperature. These two where it's hot, or sorry, no. These two right here and here, where S and W are the same values and it's only T that's different, they go together. And we end up with 0.25. Oh, that's not going to fit. And then these two values right here, where again, W and S are the same thing. The only thing that's different is T. Those get summed together. And we again get 0.25. Notice now that those don't sum to 1. So what do? Normalize. Yeah, that's that third step. What we have right now is just the marginal distribution of of W and S being set to winter. If we normalize, we get this conditional distribution. And we end up with 0.5, 0.5. Okay, so it's the same process here. Now there are no hidden variables, so the summing out step is simpler. But we are still going to have to pick rows consistent with the evidence and then normalize. I'll leave that again as an exercise. This is one where I'd say it's probably worth it to come back and do this by hand if you're a little sketchy on anything we're doing. So this algorithm, of course, has an obvious problem. Obvious because we really already pointed it out. Let's do this in the opposite order. Space complexity, first of all. The input to this problem is that entire table, which has d to the n rows. D to the n different numbers that we need to specify even how to start this algorithm. And then the time complexity, we're going to have to iterate over the whole table. And so we have also that bad. Exponentially bad means for problems of really any reasonable size, this isn't going to work at all. Which means we need some new algorithm to solve this. The new algorithm is very complicated. It's called variable elimination, and it's going to take 3 days to teach it. That's next week. But today we can look at some previews of the concepts that are going to come up. The first thing is we need a different way to specify the joint distribution. There's no way that we can solve this problem without not starting out giving you the entire thing. This is not a solution to that problem, but it's the kind of thinking that we need to get there, which is the product rule. Now, the derivation of this is kind of trivial. This is the definition of conditional probability. Just multiply p of y over there. And we have this new thing that we have a name for, product rule. Why even bother? Well, the reason is this gives us an example of how to think about a way that we can specify the joint distribution indirectly. Now, in this case, this is not actually going to be a smaller representation, but the smaller one we do come up with next week is built on the same idea, where we're going to look at some other tables that we could have, in this case not smaller, but in general potentially smaller, that when we multiply them together give us this. And so we'll see this operation a little bit more later, this table join. But yeah, what's happening in this image is you can think of probability of y as like a one-dimensional table because there's a number in there for every value y could take on, and probability of x given y as a two-dimensional table because there's one value for every value of x and one probability for every value of y, or one row for every value of y. And then the table join is going to be essentially point-wise multiply these probabilities in the right way so that you end up with this. So this is what that looks like for specific numbers. We're going to extend this to an operation on probability tables. And this is how we do that. So we have these two tables. We need to multiply them together in some reasonable way to get probability of d comma w. What do I mean by a reasonable way? Well, we know that for any individual entry in this table, we can write out this rule and we know that's true. So when we're looking at the entry right here for wet sun, how do we get that? The probability of wet comma sun is, by the product rule, equal to the probability of sun times the probability of wet given sun. So we multiply these two together and we get 0.08. And then we need to do the same thing for D being dry. So just like that, 0.09. And now in the bottom half of the table, right here, we're talking about W being rain. So we're just multiplying this value over, like that. And those go over. Oh, I totally multiplied that wrong, didn't I? Sorry. Yeah, 0.72. my bad. And then, yeah, 0.2 times 0.7, 0.14. I don't know why I'm doing that out there now. Let's do that in here. And 0.2 times 0.3 is 0.06. And notice again that if we were to kind of do the inverse operation, sort of, and go back to the marginal, we'd be summing them together. Not surprisingly, the two entries where W is sun, they sum up to 0.8, like we had on the other side. And these two entries right here sum up to 0.2. Yeah, just a quick sanity check of our numbers. But that's the operation, is basically you line these up so that the variables that are in this table are being multiplied with the rows in this table where it's equal to that same thing. Kind of hard to put into words, but hopefully this example and diagram helps out. The chain rule is a generalization of the product rule, and it looks like for 3 variables this, and for more variables this. So let's quickly just talk about why this actually works. So if we expand these two conditional probabilities here using the definition of conditional probability, what do we get? It's, here I'll write it down here, P x1 times P of x1 comma x2 over P of x1. And then if we do the third factor here, P of the joint of all 3 of them, x1, x2, x3, over the joint of just the ones in the conditional, P of x1, x2. See what happens? This cancels with this cancels with this, and we're left with just this, which is exactly what the formula says. So really all we're doing is applying that definition in a kind of inductive way. More generally, we have this product notation, and if you're not familiar with the notation, that just means try out every subsequent value of I, get this term, and then multiply all of those together. What this would actually look like if we had more variables would be just kind of exactly like this, where in our next term we'd have P of x4 given x1, x2, x3, P of x5 given x1, x2, x3, x4, etc. This is just the concise way to represent that idea. So that's the chain rule. This is another thing that is actually very important for the derivations next week, and that's the idea is we have some smaller distribution tables. We're going to build up a joint from those and then do inference. One last important probability rule, Bayes' rule. Hopefully you've seen this in some form or another. And this is one example of getting information, probabilistic information, chopping it up, and making it look like the distribution we actually are interested in. So here's the derivation. By the product rule, these 3 things are all equal. And if we divide the P of y over, we get this. So why do we even bother with a bunch of different forms of the same thing? Why is this one special? Well, this helps us solve a lot of real problems. Oh, yeah, there's Bayes, by the way, if you haven't met Bayes. That's his rule. But the thing is, in the ghost example, it's a very useful one for this. We often have what we want to compute. What is the probability of the ghost being in this position, given all my readings? What we saw in the first slide was the probability of different kinds of readings, given that you were so-and-so far away from the ghost. That is a direct specification of this P of y given x. And P of x, that's just the probability of the ghost being there at all, which we have a prior distribution over that, right? We assume, before we have any information, that it could be anywhere. And then, if we're talking about an iterative algorithm here, updating beliefs, this P of x really should be P of x given all previous evidence. And then, this is a way to incorporate the most recent piece of evidence to get an updated belief based on all of that. So that's why it's at all helpful. And yes, in the running for most important AI equation, the reason is this is the really most basic kind of reasoning that the rest of what we're going to be doing is built on. All of Bayesian networks, which is what next week and really most of the week after that is about, is generalizations of this exact idea. So before we get to the generalizations, let's work it out in a specific case. Probability of cause given effect is probability of effect given cause, probability effect. Okay, we just plug that in to Bayes' rule, right? And we can see again, probability of cause given effect, if we're talking about medical diagnosis, the cause is a disease and the effects are things that we can observe. We can come up with probability of cause by some kind of census data. How likely is it that someone might have this disease? And probability of effect given cause comes from the same place. We've seen that in 80% of cases, someone with meningitis has a stiff neck. And so given that you have meningitis, the probability you have a stiff neck is 0.8. And then you can also have a stiff neck for other reasons. So given that you don't have meningitis, probability of a stiff neck is 0.01. It's not 0, but it's not super high. And then this is 1 in 10,000 people has meningitis. So probability of plus m equals 0.0001. The point of all of that is that these are numbers that are reasonable to come by. These are the natural things that you can gather from scientific experiments and population data and these kinds of things. Once you have these three numbers, we don't have to chug through this right now, but all we're doing is, this is what we want, plug it into Bayes' rule, expand this out because we don't directly have p of plus s, but we can get p of plus s by using the product rule for both values of m and then summing out m like this. That's all we did right there. And then put in the numbers. And then, oh no, I forgot to put the number on the slide. Well, we're not going to actually work this out, but it turns out to be something pretty small. Like, basically this number right here is a lot bigger than this one. And at this point, the question is, what fraction of this whole sum of all of these is this one? And it's a pretty small one. So the point is, posterior probability of meningitis, still very small. That's an important word, actually. Posterior, I don't think we mentioned this. I've been saying prior, that's with no evidence, what I believe. That would be probability of cause, prior belief. And then we get evidence, or a conditional distribution, probability of effect given cause. And posterior is this. So prior, conditional, posterior. You'll hear the word posterior a lot more times, but it's after we've done this Bayes' rule flip around, what is the probability of the thing we want to know given the evidence we observe, posterior. And quick other aside is even if you have some really low probability of having meningitis, remember that for actually making decisions, think back to the lecture on utilities. We're talking about you assign some positive or negative utility to each outcome. If your probability is 1 in 100 that you have meningitis, but it's 2,000 times as bad to have undiagnosed meningitis as to accidentally go to the doctor's office and find out nothing of interest, then the utility will work out such that that's actually the decision you should make. So, okay, let's skip this too. Here's another intuition for Bayes' rule. This is something that has happened to me in my life. This is a very personal example. This is in the past. The numbers have changed. We're at the end of this slide. You'll see what I've learned as a result of evidence. But once upon a time, I was 90% confident that I was a good singer. And I have some numbers. These are, if I'm a good singer, 99% of people will like my singing. And if I'm a bad singer, only 10% of people will. You know, that's not exactly 1, because some people just don't like the style or whatever. That's not exactly 0, because some people just have bad taste. And so the problem is, I go into my living room and I start singing, and my roommate covers his ears. He doesn't want to hear me sing. Clearly, he doesn't like my singing. So that's some evidence, and I need to update my belief over how likely it is that I'm a good singer based on what I've learned. How do I do that? Well, putting this into probability terms, into an actual query that we want to solve, I previously had P good singer, that's my prior, and now I want this posterior P good singer given the evidence roommate doesn't like my singing. So we can apply Bayes' rule. We can even at this point just blindly stick in all the numbers. And I had hoped to actually take the chance to do that, but we're kind of out of time. So actually this is a good exercise because a lot of problems you'll see are kind of specified in this way, where you have to really think about what in probability form each of these numbers in a sentence really means. But yeah, so now I have to consider the probability of what I observed as a fraction of how likely it would have been over the alternative possibilities. In this case, that I'm not a good singer. And because in this case it depends really heavily on these two numbers, it turns out that if my roommate doesn't like my singing, it's a lot more likely that I'm a bad singer. And so once I plug in the numbers, it goes down to about 9%. And that's where we are today. Yeah, quick aside, I added this in because I think it's very interesting. I know that I said in the beginning we weren't going to talk about philosophy too much, but then yesterday I also said it's sometimes hard to tell if you're in artificial intelligence or a life help seminar. This is one of those cases. This kind of reasoning, Bayesian, and then the generalizations we see next week, it builds up this whole philosophy theory of what it actually means to know something called Bayesian epistemology. Really all that means is you have some distribution over all possible outcomes, and that manifests in your mind as a belief of how likely each certain thing is. And then you have a principled way using numbers and probabilities that you've learned based on experiences and utilities that you've assigned from some kind of elicitation process that we talked about before to come up with what is the expected utility of each decision you could make given your new evidence. And to be rational in the formal sense, you have to make your decisions based on those numbers. It's very interesting because this is, when you start using the same kind of math to apply to human decisions, that's when the nomenclature of, we have words like rationality and regret and belief, and they mean something mathematical. But here, what they actually correspond to is what we think about them meaning in day-to-day life. Being rational in this sense is being willing to change your mind when you see evidence that contradicts what you believe, like I did on the previous slide, and things like that. And you end up making decisions to maximize expected utility. That's really interesting. Sorry I'm holding you late this time. It's probably because of that feedback. But I did promise that we would see the numbers on here. So let's just see that one time and then you can go. So right now we have, what is that, probably 50 squares, yeah, that it could be in. And so our prior is uniform over all of them. We don't know where the ghost is. Take one observation. It's yellow. Yellow means it's about 3 away, most likely. So it's very unlikely now that it's really close. It's very unlikely that it's really far. You can kind of see a ring of where, according to our posterior distribution, accounting for this evidence we've gotten, how likely it is to be in each of those squares. So let's try here. Now all the probabilities kind of concentrated over here. So we're just kind of chasing this down. All right. So now not only have we said that's red, so it's really likely that it's right there, we actually have a number. We can calculate this number, and mathematically there is a 90%, 9/10 probability that that's where the ghost is. So at this point, we're probably safe enough just doing that, and we get it. And from this, we'll develop algorithms that really cleverly solve this problem in the fastest way they can. Okay, thank you everyone. And yeah, last thing, not part of the lecture really, but